Descartes' rule of signs, to find the number of possible positive, negative, and non-real solutions a polynomial equation has. For Descartes' rule of signs, what we look at is from one term to the next after it's been written in descending order, whether the sign of the coefficient in front of the term changes from one term to the next. If it does, that's called a variation. If it doesn't, then that's not a variation. Now, Descartes' rule of signs says that if you count the number of variations in sign of your polynomial equation with real coefficients that's already been written in descending order, that the number of positive roots that exists for that equation is going to be the same as the number of variations in sign, or less that by an even number. So, for us to find out the number of possible positive roots for this example, we notice it's already in descending order. We notice that the leading coefficient is positive. The next term's coefficient is negative, so it went from positive to negative, so that's one variation. Then negative to positive is another variation. Positive to negative is another variation. Negative to positive is another variation. And positive to positive is not a change in sign, so that's not a variation. So this equation has 4 variations in sign. So it has either 4 or less that by an even number. So if I take 4 and subtract 2, that would be 2. Or if I subtract 2 again, I get 0, positive roots. So that's my situations with the number of positive roots. Now, to find the number of possible negative roots, I take and run negative x through the original polynomial and then count the variations in sign. The number of possible negative roots will be the same as the variations in sign of p of negative x, or less that for an even number. So here, our polynomial is p of x is equal to 4x to the 5th minus 3x to the 4th plus 7x cubed minus 2x squared plus 4x plus 9. If I put negative x in for all of the x's, I have 4 times negative x to the 5th minus 3 times negative x quantity to the 4th, all the way through, plugging the negative x in for the x's. And now simplifying, negative x to the 5th using your order of operations, that'll be a negative x to the 5th because it's an odd exponent. And negative x to the 5th times 4 is a negative 4x to the 5th. Negative x quantity to the 4th will be a positive x to the 4th. So positive x to the 4th times negative 3 is still a negative 3x to the 4th. Negative x quantity cubed, it's an odd exponent, so that'll be a negative x cubed times positive 7, so that's a negative 7x cubed. Negative x squared is a positive x squared times negative 2, so that's a minus 2x squared. And then 4 times negative x is negative 4x, and then plus 9. So I have negative to negative is not a variation, 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 negative to positive is a variation, so I have 1 variation in sign. So I have 1 negative root. So there's 1 negative number that's a root of that polynomial equation. Now, had this come out to be something like 4, then I would have had 4 or 2 or 0 negative roots. Or if it would have come out to be 3, I'd have 3 or less that by an even number, 1 negative root. Now we take each of the situations of the number of possible positive roots with each of the situations of the number of possible negative roots. So I can make a table. If I had 4 positive roots with 1 negative root, and I see that my highest power of my polynomial equation is 5. So if I count multiplicity and the complex non-real solutions, I'll have as many answers as the highest power in my polynomial, so 5 is my total number of roots. Well, 4 plus 1 is already 5, so that would mean in that situation, I wouldn't have any non-real roots. Now, the next possibility is that I had 2 positive roots and 1 negative root. Well, my total still has to be 5. So 2 plus 1 is 3. I need a total 5, so then in that case, I would have 2 non-real roots. And then last case is if I have 0 positive roots with my 1 negative root, so 0 positive roots with 1 negative root, and I need a total of 5 roots, that would mean I would have to have 4 non-real roots. So finding the possible number of positive, negative, and non-real solutions is actually this table that shows the different scenarios that might occur for the possible solutions, the sign of the possible solution or types of solutions for that polynomial equation.